Good morning. Today we'll discuss about one of the problem solving strategy called branch and bound technique. So far we have studied that to solve an algorithm or to solve a problem, various approaches have been used. We have studied how to use divide conquer, we have studied how to use dynamic programming, along with greedy strategy also there. Beside this strategy, we are also having some different strategy, that is branch and bound technique, backtracking approach, approximation algorithms, and so on. So today I am going to discuss about this branch and bound technique. Okay. This method was first proposed by A.H. Land and A.G. Doing in 1960. This branch and bound is a systematic method for solving optimization problem. Remember, we have been using this method for solving optimization problems. What is optimization problem? Actually, it may be in mathematics or in computer science or even in economics. An optimization problem is the problem of finding the best solutions from all the feasible solutions. That is, for a particular problems, we can have so many set of feasible solutions. Among all those feasible solutions, we have to find the optimal one, the best one. So, this optimization problem can be solved using some efficient optimization technique. What are the optimization techniques are used? The various optimization techniques are genetic algorithm, simulation annealing, dynamic programming, linear and non-linear programming, and so on. So branch and bound is one of them. So let us come to branch and bound technique. It is an optimization technique applied where the greedy method and the dynamic programming failed. However, though it is a slower process, but sometimes it leads to an exponential time complexities. That means this problem is used, or this technique is used to solve a particular class of problem. That means for some particular problem, this method is more suitable than these greedy and dynamic approaches, and also it takes less time than those approaches. Okay, so today I'll discuss some of the problems that we can able to solve using branch and bound technique. Okay. So let us start with 0 and 1 knapsack problem. 0 and 1 knapsack. Actually, knapsack means a bag. Knapsack means bag. So what is the knapsack problem? Actually, given a set of items, let it be I1, I2, I3, in, and let me write items, let it be I1, I2, I3, in, given a set of items, each item is having a weight, let it be Wi. Each item is having weight and value, let it be Vi. So each item I1 having some weights and having some value. The objective of 0-1 knapsack problem is to choose xi, a part of the item. Xi means a part of the item such that summations of such that summations of wi xi should be less than equal to m. What is m? The m is the size of the bag. Okay, and summations vi xi should be maximum. So I am repeating what is knapsack problem or 0-1 knapsack problems. Given a set of items I1, I2, In along with their weights, let it be W1, W2, Wn, and the value V1, V2, Vn. The objective of this 0-1 knapsack problem is to find the portions of the item that is called xi, the portion. This is the portion of the item. Portion of the item xi such that wi xi should be less than equal to m and vi xi should be maximum. What is xi? Xi is the portion of the item. Portions of the item, that is xi is either 0 or 1. That means if it is 0, it means I am not going to take that item. If it is 1, that means I am going to take the whole of the item. But remember, in 0-1 knapsack, the xi cannot be a fraction. That means I cannot take a fraction of the item. Okay. So how to solve this problem? 0-1 knapsack problem can be solved using dynamic programming. We have already solved this. But now, today, I am going to explain a method, that is how to solve this 0-1 knapsack problem using branch and bound technique. Okay. So in branch and bound technique, we have to construct a tree first. And tree is having some branch, and in each branch, I have to specify some boundary conditions. How it is? Let me explain this once. Let us take an example. Let us take an example. Suppose item, this is weight, this is value, and bag size is given, suppose 8. Bag size is given 8, that is knapsack size, item W and V. Suppose items are A, B, C and D. 4 items are there, each having weight. Let us assume that W is having 2 kg, A is of 2 kg, whose value is 40 rupees. Similarly, B is having weight 3 kg and value is 50 rupees. 50. C is having 2 kg and value let be 100. And D is 3 kg, whose value may be 95. So from this problem, we have to find the solution of this problem so that I cannot take more than the size of my bag, more than the size of my knapsack, it is 8 kg, and my profit or value must be maximum. Okay. So let us construct a tree first. So how to construct the tree? So to construct the tree, we have to take a node. Let it be root node. This is root node. So every time, this is root node, every time I have to take two path. What is this? Is for inclusions. This is for inclusions and this is for exclusions, or you can say it is in and this is out. Initially I don't have any value. Let us first I choose A. Item A is included. Okay. So when item A is included, since the weight of A is 2 kg, now my weight becomes 2 and my value becomes 40. Now out or exclusion of A. Look at here. First inclusion of A and exclusion of A. Inclusions means I am going to take the item A, and exclusion means I am not going to take the item A. If I take A, my weight becomes 2 and my value becomes 40. If I don't take A, so my weight becomes 0 and value becomes 0. Now again, now I am going to again include B. So this is exclusion of B. Okay. Again, this is inclusion of C and this is exclusion of C. This is inclusion of D. This is exclusion of D. So at each stage I have to calculate my weight and value. So look at here. At A, if I take A, my weight becomes 2 and B becomes 40. Now again, if I am going to take B, already I have my weight is 2 kg I have with me. Now if I take B, since B's weight is 3, so my total weight becomes 5 and value becomes, it was already 40. Now B's weight is 50. So 40 plus 50, it becomes 90. Look at here, it's 90. Here it was. Now if I will not take B here, if I will not take B, already taken A and not going to take B, my weight remains that 2 and value becomes 40. Similarly, now if I will take C, inclusion of C, so my weight was 5 here. If I am going to take C, since C's weight is 2, so weight becomes 7 and value becomes 190. If I am not going to take C, my weight remains 5 and value becomes 90. In D, if I am going to take D, so it was 7, it was 3, so weight becomes 10 and value becomes whatever it may be, 190 plus 95. But since my weight is 10, but I am allowed to take only 8 kg, so it is exceeds here, so it is not considered since my weight becomes 10. Now if it is out D, it remains same and V is equal to 190. Similarly, for this C, again I have to in D and out D. Let me write it once again. It was 7, B was 190. In D and out D. So here weight was 5, now in D is included, so weight becomes 8 and value becomes 90 plus 95, it is 185. Out D, plus W is equal to 5 and V is equal to 90. So I have calculated only these portions of the tree. Remaining portions are need to be explored. I have not taken that one. Look at here. Exclusion of B. Weight was 2, value was 40. Let me plot like this. It's out B. Here weight was 2, value was 40. Now inclusion of C and exclusion of C. What is the value now? Look at here. If C is included, my weight becomes 2 plus 2 4 and value becomes 140. This is inclusions. Now 140. Similarly, if I'll include D, what is my weight? My weight becomes 7. Here my weight becomes 7 and value becomes 140 plus 95. 140 plus 95. That is 140 plus 95, 235. Here. And out C, here we have weight is equal to and V is equal to 40. If it is out D, it remains same. So like this, I have to calculate each inclusions and each exclusions. Look at here, I have only drawn a half of the tree. The rest half has to be drawn. But remember, at the leaf node means at the end of the tree, leaf node, I am getting a solutions. These are called the feasible solutions. So from these feasible solutions, I have to find out which one is the optimal one, which one is the best one. Look at here the solutions. Here the solution is weight is greater than 20, so I will not pick these ones. Here my weight is 7, my maximum limit was 8 kg, but my profit or value is 190. Here it is 185. Here it is 90, but here it is 235 and weight is 7. Look at here. This seems the best solutions here. But remaining portion of the tree is still unexplored. But now I got the profit is 235, which looks more efficient, and weight is 7 kg. Still 1 kg bag is vacant, but it is the problem of 0-1 knapsack. I cannot take a fraction of it. Either I have to take full item of it or I don't take it. So which items should I take and which items should I leave? Look at here. For this to reach these solutions, I have included A, excluded B, included C, and included D. That means I have included A, excluded B, inclusion of C, and inclusion of D. So this value xi here is 1, here it is 0, this is 1, this is 1. So I have found xi. So how much profit? What is my value I am getting here? Look at this tree. You have to construct the entire tree actually. Since there is no space, so it becomes congested. So I have done only the half portion of the tree. The rest portions you have to do. I put a question mark there. So look at the solutions. Now the total weights Wi xi. Look at here, Wi and xi. 2 into 1, 2 plus 3 into 0 plus 2 into 1 plus 3 into 1. If I add this, it becomes 2 plus 2 plus 3. It is 7 kg. That means my weight is 7 kg. As per the conditions, it should be less than my bag size, and bag size was 8 kg. And profit I got is VIXI, that is 40 into 1 plus 50 into 0 plus 100 into 1 plus 95 into 1. It is 235. So this is the maximum profit. So solution is 1011 and profit is 235. So as I have discussed, the branch and bound technique is used to find the best solution from the set of all the feasible solutions. So in the leaf node, I am having all the feasible solutions, and from these feasible solutions I have to find a optimal one. Okay, so now let us go deep into these portions of 01 knapsack problem, and I will explain how you will solve this problem when some question will come in the exam. Let us solve this problem from exam point of view. Okay, so I am omitting this one. Let us take a small example. Okay, the question is this is item, this is weight, this is value. Okay, item, let it be I1, I2, I3. I am taking small examples. 3 items are there, and weight is given. Let it be 5. This is 4. This is 3. Value, let the value of the first item is rupees 6, and it is rupees 5 and rupees 4. Okay, and the bag size is given M is equal to 7 kg. So you have to solve this knapsack problem using branch and bound technique. Okay, so let us start. Let us go to the step 1. So this is step, let us go to the step 1. This is the thing given: item I1, I2, I3. Weight is given, W1 is 5, W2 is 4, W3 is 3. Then VI is 6, V2 5, V3 4. Bag size M is 7. So what I have to do, you have to find PI, that is profit. PI is VI by WI. So if the cost of item 1 for 5 kg is rupees 6 per kg, it is V by 6 by 5, that is 6 by 5, it is 1.2, I think. Similarly 5 by 4 for item 2, 5 by 4, it is 1.25, and 4 by 3, it is 1.33, I think. Okay, or 1.3, let us. Now step 2. Okay, I hope it will be clear for you. 3 items are given. I have just found the profit, that is VI by WI ratio. So now I have to arrange the items in the decreasing order of their profit, PI. That means first I write this one, then this one, then this one, decreasing order. So let me change this one. So item, so my item is I3, weight was 3, value was 4, and PI was 1.3. Look at here, after step 1 what I have done. I am arranging the items in the decreasing order of their PI. The items whose profit is maximum will written first. Next item profit is I2. Item 2, this value is 4, sorry, weight is 4, value is 5, it is 1.25, and last one is I1, it is 5, 6, 1.2. This is step 2. Okay, now we'll go to step 3. While solving 01 knapsack problem using branch and bound, you know that we have to construct a tree first. Every tree is must having a branch. At each node of the tree, I have to put some boundary conditions. That's why the name is branch and bound technique. So how to put boundary conditions? You have to remember a formula. What is that formula? Remember, in branch and bound, while solving 0 1 knapsack problem, each node will be in this format. Each node. This will be for weight, this will be for value, and this will be for upper bound. UB is for upper bound. How to calculate upper bound? The upper bound formula is that V plus M minus W into Vi by Wi, or you can say Vi plus 1 by Wi plus 1. This is the formula. V subscript I plus 1 by Wi plus 1. Okay, yeah. Please note it down. This is the way how you will solve this problem. Step 1, the problem will be given to you. You just calculate the Pi by using Vi by Wi. Then arrange the items in the decreasing order of their profit. Then in step 3, you have to represent each node of the tree by this format. 3 parts. Every node is having 3 parts. This W, V and upper bound. Okay. So let us draw the root node. So the root node, I am having 3 values. That is W, V. Look at here. So initially W is 0, V is 0, because I have not taken any items. I have not chosen any items. What about upper bound? As per the formula, upper bound is equal to, what is the formula? Just check it, your copy. V. V means it was 0 plus M. M was 7. M was given 7. Knapsack size. M was 7 initially given. Okay, this was M was 7. So V was 0, 7 minus W. W was 0. So how much it will be? Let me write here. V plus M minus W into Vi plus 1 by Wi plus 1. This was the formula. So V was 0 here. M was 7 minus W was 0 into Vi plus 1 by Wi plus 1. Since I have not taken anything, the first value, so I value is 0. Initially I value is 0. So V1 by W1. So look at here, after the order has been changed in step 2, the V1 by W1 is 1.3. This one. This is first item, 1.3. So into 1.3. So 1.3 into 7, that is equal to, I think, 1.3 into 7 is 9.1. So upper bound is 9.1. So this is the root node. Okay. Then I have to go for inclusions and exclusions. That is in and that is out. Okay. So let us, 3 items are there. Let us first include I3. So inclusion of I3 and out of I3. Let it look here. Just remember how we have to construct the tree. I have already explained to you. So one is inclusions. Left hand side I have inclusion part and right hand side I have exclusion part. So while I have to include I3, so my weight, it was 0. Since I3 weight was 3, so my weight becomes 3 and my value becomes 4. And what about upper boundary? What is upper boundary? So remember here, you have included I3. You have taken this item. You have taken this item already. Okay. So first item has been taken. So I becomes 1. Remember, I becomes 1. So what is the formula of upper boundary? Upper boundary is equal to V. V was now 4 plus M minus W. M was 7, W was 3. So here the upper boundary was 4 plus M is 7 minus W is 3 into Vi plus 1 by Wi plus 1. So since in this case I was 0 initially, but here since I have included I3, already first item has been included, so I becomes 1. So my Vi plus 1 becomes, I becomes 1, so V2 by W2. V2 by W2 is 1.25. Second. So which becomes, just calculated, I think 7 minus 3 is 4. 4 into 1.25, it is 5 plus 4, it is 9. Upper bound is 9. What about exclusions here? Out of I3. So weight was 0. V was 0. Upper bound will be changed because what is the formula of upper bound? That is V plus M minus W. W was 0, so it is 0 plus 7 minus 0 into since we are excluding I3, the first item, that means you have to consider second items, so it is 1.25. In case of 1.3, it is 1.25. so it becomes, I think, 1.25 into 7, maybe approximately is 8 point something, 8.75 maybe. You just calculate, check it out. Okay, now inclusion of I3 and exclusion of I3 was over. Next, remember, this is how you have to solve the problem during exam time. Okay, next, inclusion of I2 and exclusions of I2 or out of I2. Okay, so initially weight is 3, V was 4. If I take I2 weight was 4, so my new weight becomes 3 plus 4, it becomes 7, and V becomes, it was 4, now it is 5, so V becomes 9. Actually problem is that I am holding my mobile cell phone in one hand, in left hand, and solving the problem right hand. I think it is inconvenient for you, so better you solve yourself in the paper, then it will be easier for you, and verify the answer. Okay, so W becomes 7, B becomes 9. What about upper bound? So now upper bound is equal to, what is the formula? Now here, look at here, I will include I3, I have included I2, the last option is item I1. So here upper bound is the formula, as per the formula, V plus M minus W. V was, here V was 9 plus M was 7 and W was 7. So 7 minus 7 is 0 into the Vi plus 1. First item, second item has been chosen. So next I becomes 2. So I plus 1 becomes 3. So V3 by W3 is 1.2. So it is 0. It becomes 9. Exclusion of I2. So W becomes 3. V becomes 4. No change there. But we will have change in upper bound. Upper bound. So what is upper bound? Again apply the formula, same formula. It is 4 plus 7 minus 3 into 1.2 here. It is 1.2. Now I am getting the value. How much it is? 4 into 1.2, that is 7 minus 3 is 4. 4 into 1.2 is 4.8 plus 4, it is 8.8. Now come to that side, the right hand side. Here out of I3 has been excluded. Next is inclusion of I2 and exclusion of I2. So when initial weight was 0, now if I include I2 whose weight is 4, so my weight becomes 4, V becomes 5, V becomes 5, and upper bound becomes, as per the formula, it was V plus M minus W. V was 5 plus M was 7, 7 minus 4 is 3 into exclusion of I2, so again I have to put 1.2, so it is 5 plus 3.6, so it is 8.6. In exclusions, again weight is 0, V is 0, V is 0, weight is 0, V is 0, and 0 plus 7 into upper bound is equal to 0 plus 7 into 1.2, so versus 8.4. Okay, so then I'll go for, look at here, in first root node nothing I have taken, in the left side inclusion of I3, exclusion of I3, then inclusion of I2, exclusion of I2, then I'll have inclusion of I3 here. But remember, if I include I3, inclusion of I3, what will happen? Inclusion of I3, so weight was 7, I3 weight was, sorry, inclusion of I1, sorry, I3 was here, then second number is I2, third is I1, inclusion of I1, so my weight becomes 7 plus 5, it is 12, so weight becomes 12, so it is not allowed because my bag size is, my knapsack size is 7 only, I cannot take these ones. Already I have achieved the weight that is 7. So here next inclusion of I3, then exclusion of I2, again inclusion of I1, here again similar inclusion of I1. What will happen? Inclusion of I1, it was 3 plus I1, I1 weight is 5, now my weight becomes 8, which is again not allowed. I need not have to calculate the value of V and upper bound here because my weight is exceed here. Okay, so this side I am getting some solution. Look at here, I am taking I3, then taking I2, and not taking I3. If I take I3, sorry, not if I am taking I1, I am getting weight 12, which is not acceptable. That means this is a solution I am getting. This is one solution. What is solution? Weight 7 and upper bound is 9, value is 9. Here 1 is included, a 3 is included, item 3 is included, item 2 is included, and item 1 is excluded. Okay, next here I am not getting solutions, so here I will inclusion of I1, the same value I will have here, W3 and V4. So here value is 4, weight is 3. So if I compare these two solutions, this one and this one, here weight is 7, V is 9, here weight is 3 and V is 4. This is 4. So which one is better? So this one is the optimal one. This one is the optimal one. Similarly, in that side, you can check it. You will never get a value where the value is 9. Definitely, we are getting the upper bound or value. Upper bound here is 9, here is 8.6, here is 8.4. You will not get more than that value. That's why this is the feasible optimal solutions. So from this tree, it is clear that inclusion of I3, that means I have to write 1 here, I2, again I have write 1 here, and exclusion of I1, that is 0 here. So what is the solution? So look at the problem first. So now the solution xi, here I have to take 0, I will not take I1, I have to take I1, this one. So what is the maximum value? So maximum value is 6 into 0 plus 5 into 1 plus 4 into 1. So 5 plus 4, 9. So answer is, maximum value is 9. This is the solutions, and answer is 0, 1, 1. So the way we have solved this problem is called branch and bound technique. That means we have to construct a tree, and each tree, at each node I have to specify the upper boundary conditions. Remember the formula for 0, 1 knapsack problem. The upper boundary condition is V plus M minus W into Vi plus 1 by Wi plus 1. What is V? V is the value, M is the knapsack size or bag size, W is the weight, and Vi plus 1 by Wi plus 1 is the ratio of the profit of the next item. Okay, I hope you can go through this video and you can able to understand, and if you have any doubt you can text me, and I am giving one assignment also. Let us solve this problem. Okay, I'll also give some assignment. First you go through this video. If you are comfortable, then text me, then I'll give the assignment, and in the next class we'll meet for another sessions. Okay, thank you all.